Have you ever wondered how the devices around you, like your smartphone or laptop, are powered? Welcome to the fascinating world of electricity, an essential form of energy that brings life to the myriad of devices and systems we use every day. At its core, electricity is generated by the movement of tiny particles called electrons. Imagine these electrons as a bustling crowd of people moving through a city's streets. The city is our conductor, and the crowd's movement represents the flow of electricity. Now, what gets these electrons moving? That's where a potential difference, or voltage, comes in. Think of it as the motivation that drives the crowd to move from one place to another. From lighting up our homes to powering our computers, electricity is a fundamental aspect of our lives. And it all starts with the simple movement of electrons. So power up your thinking caps as we dive deeper into the world of electricity. Imagine a racetrack. Can the cars race without a defined track? Certainly not. Similarly, electricity needs a path to flow, and we call this an electric circuit. An electric circuit is like a highway for electrons. It's a closed path or loop that allows an electric current to flow. Picture cars moving along a circular racetrack, always returning to where they started from. That's essentially how electricity moves through a circuit. Now, no highway is complete without its essential components, right? The same goes for an electric circuit. Let's talk about these components. First up, we have the voltage source. Think of this as the fuel station for our electron cars. A voltage source, like a battery or generator, provides the potential difference or push necessary to drive the electric current. Next, we have the conductors. These are the roads that our electron cars travel on. Conductors are materials, such as wires, that allow the flow of electric charge. Then, there's the load. This is the destination for our electron cars, where they do their work. The load is a device or component that converts electrical energy into other forms. It could be a light bulb emitting light, a motor turning, or a heater warming up. Finally, there are switches. These are like the traffic signals of our circuit. They control the flow of current, allowing it to either move or come to a halt. And just like how cities have different road layouts, we have different types of circuits. In a series circuit, components are arranged sequentially along a single path, like cars on a one-way street. In a parallel circuit, components have multiple paths for current flow, much like a multi-lane highway. So, in essence, an electric circuit is a complex system that involves a voltage source, conductors, a load, and switches. It can be designed in a series or parallel configuration depending on the requirements. Now that you know about circuits, let's explore what flows through these circuits. Ever seen a river flow? That's exactly how electric charge flows, and we call this electric current. Imagine a bustling city, its streets filled with people. Now think of these people as electric charges. Their movement from one place to another, like the ebb and flow of a bustling city, is what we call electric current. But instead of people, we're talking about tiny particles called electrons zipping around at incredible speeds. Electric current is the lifeblood of our modern world, powering everything from the smallest watch battery to the largest power grid. It's the flow of electric charge through a conductor, like a copper wire. This movement of charge is what lights up our homes, powers our devices, and keeps our world humming along. Now let's talk about how we measure this flow. Just like you'd measure the flow of water in liters or gallons, we measure electric current in a unit called amperes, often shortened to amps. Named after the French scientist André-Marie Ampère, an ampere represents 1 coulomb of charge flowing per second. In the world of electricity, we denote current with the symbol I. Why I, you ask? Well, it's a nod to the French term intensité du courant, or in English, current intensity. And how do we measure this current, this flow of electric charge? With a handy device called an ammeter. An ammeter is connected in series in the circuit, and it helps us to measure how much current is flowing at any given point. So, to sum it all up, electric current is like a river of charge, flowing through the conductor, measured in amperes, denoted by I, and gauged using an ammeter. It's a fundamental concept in electricity, and understanding it is key to unlocking the secrets of how electricity powers our world. Great! We've got a grip on electric current, but what drives this current? Let's find out. What makes a ball roll downhill? It's the difference in height, right? Similarly, it's the potential difference, or voltage, that drives the electric current. Just as gravity acts on a ball to move it from a higher position to a lower one, voltage is the force that pushes electrons, thus creating an electric current. It's the driving force behind the flow of electric charge in a circuit, the unseen push that gets things moving. Now, if we want to get a bit technical, voltage is defined as the energy transferred per unit charge. In other words, it represents how much work is done to move an electric charge from one point to another within a circuit. The greater the voltage, the greater the force or push moving the electrons along. Voltage is measured in units called volts, named after Alessandro Volta, an Italian physicist who was a pioneer in the study of electricity. This unit of measurement, abbreviated as V, gives us a way to quantify the potential difference in an electrical circuit. The symbol we use to represent voltage is V, and we measure it using a tool called a voltmeter. This device is connected across the points between which the voltage is to be measured. It's like a ruler for electric potential, helping us measure how much push there is in a circuit. But there's an important aspect to remember about voltage. It doesn't exist on its own in a circuit. It's always associated with a flow of electric current. Think of it like the slope of a hill. The steeper the slope, the faster a ball will roll down it. Similarly, a higher voltage will push more current through a circuit. So in a nutshell, voltage or potential difference is the work done to move a unit charge from one point to another. It's the driving force in an electric circuit, measured in volts and represented by the symbol V. So voltage is the push that drives the current, but how are voltage and current related? Enter Ohm's law. Ohm's law is the superstar of electricity. It's the rule that defines the relationship between current, voltage, and resistance. This law is named after the German physicist Georg Simon Ohm, who first formulated it in the early 19th century. So what exactly is Ohm's law? Well, it's quite straightforward. Ohm's law states that the current flowing through a conductor is directly proportional to the voltage applied across it, given that the temperature and other physical conditions remain constant. This means that if you increase the voltage, the current will increase. And if you decrease the voltage, the current will decrease, as long as everything else stays the same. Now let's dive into the mathematical formula for Ohm's law, which is quite simple. V equals 1 times R. Here, V stands for voltage, I represents the current, and R is the resistance. This formula can be rearranged depending on what we want to calculate. If we want to find the current, we can divide the voltage by the resistance, that is I equals V divided by R. And if we want to find the resistance, we can divide the voltage by the current, so R equals V divided by I. This law is tremendously useful in understanding how electrical systems work. For instance, if we know the voltage and resistance in a circuit, we can use Ohm's law to calculate the current. Conversely, if we know the current and resistance, we can calculate the voltage. And if we know the voltage and current, we can figure out the resistance. It's like a jigsaw puzzle, where if you have 2 pieces, you can easily figure out the third. Ohm's law is used in a countless number of applications, from designing electrical circuits to troubleshooting problems in electrical systems. So, remember, whenever you're dealing with electricity, keep Ohm's law in mind. As long as the conditions are constant, current, voltage, and resistance will always obey this law. With Ohm's law, we can now understand and analyze any electrical system. Now let's bring it all together. We've journeyed through the fascinating world of electricity, a fundamental energy that powers our daily lives. We've discovered that it's all about the movement of electrons, driven by a potential difference or voltage. We've navigated the intricate pathways of an electric circuit, a closed loop that allows electric current to flow. We've identified the integral parts of a circuit, the voltage source, conductors, load, and switches. We've also explored the different types of circuits, series and parallel. We've delved into the concept of electric current, the flow of electric charge, measured in amperes. We've learned about voltage, the driving force of electricity, measured in volts. Lastly, we've unraveled the mystery of Ohm's law, which tells us that the current flowing through a conductor is directly proportional to the voltage applied across it, and that's a wrap. With this knowledge, you can now look at the electrical devices around you in a whole new light.